Okay, this is lecture number 7, and the objective of this lecture will be to discuss about hotspots. So this lecture has more of an emphasis on extensional tectonics. So we are going to discuss the process of formation of plumes, as well as exploring some of the products that are related with plume magmatism. Not that we haven't really talked about shield volcanoes previously and how they develop, but it is important to strengthen the relationship between this type of volcanoes and key volcanic products, and also understand why certain volcanic products are associated with others, their order, for example, the stratigraphy of shield volcanoes is important because it gives a good way to distinguish this this tectonic setting from others. Beside this, also it's important to realize that there are more complicated scenarios in which we have combinations of the tectonic environments that we discussed. So we will make an example with Iceland, which is on the Atlantic Rift, but is also a good example of the localization of a hotspot in overlap with a major oceanic ridge. So that's of course affecting the intensity of magmatism and the type of processes that lead to the formation of magmatic products. So it's important to look at the evolution of Iceland and provide sort of an example of this complexity. So this links up with the previous lecture in which we were talking about different types of volcanoes. So we continue the discussion on volcanoes, but emphasize some of the core processes that crustal scale processes that leads to the formation of volcanoes, and also understand, as I said, their complexity. So let's dig into the mantle plumes and hotspots. Mantle plumes are essentially related to the convection processes that take place on our planet, in particular the convection that takes place in the outer core as well as the lithosphere. So asthenosphere and lithospheres and their interaction will lead to the production of these mantle plumes. You have to think at the process of formation of a mantle plume as a very slow magmatic process that leads to the formation of a main feeder that provides magma that usually has a lower density than the surrounding mantle, and from the asthenosphere we have this rising mantle plume that will concentrate at the bottom of the crust. So mantle plumes will create hotspots because you have essentially an anomalous geothermal gradient that is imposed by the plume because the magma is hotter than the surrounding lithosphere. And this of course will result in high heat flows, volcanism, and in some cases crustal swelling. A plume evolves in two main stages. We have the starting of the plumes, which, as I said, will develop essentially a bulbous head that rises through the mantle, and then the head, when it reaches the area where there is more contrast with the lithosphere, it will essentially deform and form a mushroom-like geometry, and where we have sort of the majority of the partial melting taking place. We will see an example of that with Yellowstone. So the second stage will be marked by the effect of a still rising but much narrower tail. This is, quite often the result of the mixing of ultramafic magmas with the other magmas that are resulting from the partial melting. Basaltic magma is created because of the process of decompression. So if you remember, when we lower the pressure, we facilitate melting, and this will also contribute to assist in the rising of the hot plume because you have less resistance. So an extensional regime quite often promotes the accumulation of mantle magma very close to surface. The plumes are quite distinctive and usually show hints of being derived from ancient subducted slabs. So often we argue that some of the slabs get trapped at the boundary between the mantle and inner core, or between actually the lithosphere and asthenosphere. So those two boundaries most often is the second one. So the interface between lithosphere and mantle will be sort of hosting these slabs. And when you form a plume, what happens is that you partly get the magma contaminated by these islands of or remnants of oceanic crust or continental crust, depending on the type of subduction. So this is important because it tells us that these are deeper, relatively deeper sources, and they can be quite complex or subjected to quite complex processes of assimilation of a pre-existing crust, which, for example, render this rock in some cases particularly rich in volatiles and, for example, CO2, or they usually have unusual alkalinity. We saw some examples of kimberlites which were classified as ultrapotassic rocks. So if we move on and talk about some of the major concepts, a starting plume that rises beneath the ocean floor produce a large plateau or a floating basalt. So we do not exclusively form volcanic islands. We can form also these major plateaus, and these quite often will form when you have an extended plume, so a large head basically. Volcanic islands will form instead above the tail of the plume, so where you have the majority of the heat dissipation, and this usually is a process that is like a dotted process. It takes a specific location for a certain time, and then when the plate moves, this location changes. So this leads to trails of islands that are a good indication of the plume activity. We will see again the example of the Hawaiian Islands, which should now be quite obvious as a phenomena for the formation of shield volcanoes that are in sort of trains depending on the movement of the plates. If a plume develops beneath a continent, well, you will form what is found in the States on the western coast, where you have the Yellowstone calderas. So we have those Columbia flowed basalts that are really extensive, and usually they will be associated with regional uplift and also the formation of these calderas. We'll see that the calderas are usually the result of a relatively shallow crust partial melting that creates voids and depression because of the movement of magmas from one chamber to another, and this is linked similarly to the Hawaiian volcanoes to the movement of the crust. Plumes may affect also larger systems, so the climate with the intensive eruptive activity. So Yellowstone was one of the most relevant eruptions in the history that we know of, with a VEI of 8, so quite tremendous. So if you make a comparison, it's much bigger than Krakatoa and the Vesuvius, and also eruptive activity can influence the magnetic field as well. So the example of the Yellowstone caldera is here in cross section. We have essentially that a mantle plume can occur underneath a continent, in this case North America, and it will generate usually a bimodal magmatism. So this is an important concept. Bimodal magmatism is usually composed of two end members. One is a mafic end member, so basalts, and the other is a felsic end member, so the rhyolites. So if we talk in terms of volcanism, in terms of intrusives, usually we have gabbros that form in magmatic chambers that are relatively deep, and you have here in this example for the Yellowstone a depth that is estimated on the order of 100 kilometers. So we start to have these small pockets of magma forming, and these will progressively rise. But these are, sometimes you have magma ponding here, and so you form intrusives that are dominantly gabbroic in composition, and while you move up, you get that the magma fractionates, and you end up here in the crust, which is continental crust for this example. You tend to have silicic magmas forming because of the abundant partial melting of the crust. You still have basaltic rocks in here, but they are linked to these deeper magmatic chambers, and so you form dike complexes that are mostly doleritic in composition, so basaltic, and these will result in vertical dikes and horizontal sills, basically. So these are the large basalt lava flows, so the sources will be these deeper sources. Instead, rhyolite ash and caldera activity will be linked to these more granitic intrusives and more rhyolitic complexes that will essentially manifest with the Plinian activity, or super Plinian for the Yellowstone caldera specifically, with super large eruptions started at, I think, 600,000 years ago or more. So remember this dualism. Usually you have both basaltic flows but also Plinian activity in continental hotspots. Here is an example that shows the influence on the crust of a major plume. So a mantle plume will appear to be extended. It usually has nearly vertical columns of hot upwelling materials that will rise from deep in the mantle. At the surface, the plumes are marked by hot spots with high heat flow, volcanic activity, and broad crustal swells. The crustal swell is exemplified in here. Sometimes this elevation reaches roughly a kilometer, just to give you the feeling of the scale, and there is a relative movement of the crust, so the hot spot will stay relatively steady and the crust will move progressively. Here is an example of a geophysical mapping of the plume under Iceland. So I was mentioning this more complicated case. However, geophysicists using seismic, they can actually map the temperature gradient and the anisotropy that exists. And so they can essentially map out this volume that is at relatively higher temperature if compared to the surrounding mantle. And so you can see that this is a relatively deep process which forms this hot column of magma that is upwelling and resulting in extensive and continuous volcanism on the surface of Iceland. So this relationship with temperature usually leads to low seismic wave velocities. So hot materials tend to have relatively low seismic velocity, and the plume usually is, as I stated, hotter than the surrounding mantle. Just to repeat that so that it's clear. Another example here for mantle plumes is the Hawaiian Islands. I won't spend much time on this because we talked extensively about these. We'll see that erosional processes are quite important while you get to older islands, and the fact that you have a plume that is extending in one direction and has its core on the big island is actually influencing also the degree of magmatic activity that takes place away from the center. This slide illustrates the evolution of mantle plumes. So we have to think about the complexity of interactions, and we are going to discuss these different environments and the implication, for example, of crustal contamination. So you see an example here of break-offs of slab that gets entrained in the mesosphere, and so it's basically dipping until they reach the boundary between the outer core and this mesosphere. So let's discuss this later. The majority of the plumes will rise from the core mantle boundary. So you have here a good diagram that shows this boundary, and you can see different stages of plume development. Not all the plumes will be departing from this boundary. There are some exceptions that actually depart from this other interface, which is the interface between the asthenosphere and the mesosphere. So in this diagram we see different tectonic settings. So we have an island arc, fluid basalt province, mid-oceanic ridge, a hot spot, and another island arc. In here it gives you the sense of the recirculation of crust that is recycled, as well as magmas that are rising, and they are indicated by these blue arrows that indicate the flow of the magma either in the lithosphere or asthenosphere or mantle in general. I think it's important to emphasize this process of termed avalanche of slabs. Sometimes the slab will be almost intact until it reaches this boundary. Some other times there is a breakup that takes place, and this breakup will form little islands of remanent crust that can reach the interface between the outer core and the mantle. So it is claimed that some of these islands will interact with this plume, for example, and this will lead to changes in the composition. For example, enrichments in sodium and potassium are quite common in these magmas. We saw kimberlites as a good example of that, but also other things like lamprophires will have in general more potassic compositions. Other things that are of interest is this other process. So you see this mushroom-like bulbous head extending laterally, and this sort of justifies the extent of flowed basalt provinces. For example, the Columbia basalts we saw in a previous lecture are a good sort of example of a process that is linked to this deeper source of magmas that are mostly basaltic in composition. So that's connected also with the example of Yellowstone. So remember that bimodal magmatism, that's a good example of that. And this last example here is more an illustration of the effect of hotspots. Over time, you will lose the tails of the plume, and you start to have the more focused supply of magmas in a restricted location, and this leads commonly to the formation of the shield volcanoes. So you can see other shield volcanoes here that are essentially getting away because of the plate motion, and so you lose the source of the magma, and this becomes many times seamounts with the development of atolls quite often. So this is a good summary, I think, of all the processes we have been discussing in the past few lectures and the relative tectonic settings. So in light of the shield volcanoes and flowed basalts, we can see how plumes evolves over time, and also get a perspective really of two things: how the temperature of the plume head changes over time, as well as how long it takes actually to physically produce a plume and get it to surface so that it can interact with the crust. So the crust is here, so it's a relatively thin layer of silicates that is separated from the mantle by the Morovicic discontinuity. So at 0 million years we start to develop the plume. Quite often you have a neck with a bulbous head that starts to develop, and one of the things that always happen is that the bulbous head will and drain part of the adjacent mantle. This process takes roughly 40 million years, and the pressure exerted by the plume tends to increase also the uplift of the crust, which usually reaches 500 meters over 40 million years. So it's a process called surface unwarping. The maximum elevation is reached roughly at 60 million years, which is the time at which the bulbous head gets flattened because of the contrast encountered when it reaches this colder lithosphere. So lithosphere starts to interact and partial melting develops in the lithosphere, and so we have this production of bimodal magmas in continental settings, or dominantly basaltic magmas or tholeiitic magmas in the shale volcanoes, so in hotspot related activities. Subsequent processes will lower the zone of high temperature progressively. So while the plumes matures, you get an asymmetry developing, and this is reflecting also on an asymmetry of the thickening. Remember that any instability in terms of thickening in the crust is usually compensated by erosional processes. So if you create a bulge on the surface, it takes really tens of million years to remove that through weathering and erosional processes. And this is what is happening in this example. We are losing roughly 700 meters of surface thickening. And we also introduce an asymmetry that is related to the effect of the redistribution of mass that occurs in the plume. And here we also further reduce this, and this corresponds really to the erosional process and submerged condition in which a shield volcano enters towards the end of its life. So at 100 million years, you can almost see that there is no longer volcanic activity taking place on a sort of dead shield volcano, and mostly you have an atoll with corals that develops on top where originally the crater was located. And also usually the volcano is more depressed, and in response to that it becomes a submarine or seamount form, which is then conquered by sea life. Here we change the subject slightly, and we look at distinctions of tectonic settings based on different types of magma. One way of discriminating magma is by looking at enrichment in specific chemical elements, which are sets of majors and trace elements. Quite often shield volcanoes that are located on hotspots are quite distinguished from subduction related magmatism, so island arc basalts, for example, and also mid-ocean ridges, which are also basaltic in composition. The major difference is the enrichment in specific elements. So you see there a few relatively large cations, so larger than other cations. For example, titanium is quite small, zirconium will be quite small, but barium, potassium, those are and calcium and cerium are quite large cations. So they tend to be incompatible, and because of that they usually end up getting fractionated away, and so a melt will tend to essentially fractionate and keep these volatiles and incompatible elements, and also other things will enter into these magmas, which includes rare earth elements. So in this example you see this blue curve that shows 50-time enrichment in some of these elements that I just mentioned, which is a good way to distinguish really ocean island basalts from island arc basalts and mid-oceanic ridge basalts. Of course, there is also a trend, so ocean island basalts are more smooth. Instead, island arc basalts will be more zigzag trends, so more complicated trends. For example, if you look at the niobium, there is actually a correspondence between niobium in island arc basalts and mid-oceanic ridges, and a major difference because here it's a peak in the ocean island basalts. So some of these trends can be used for discrimination purpose, and they will help you differentiating the different types of sources. So of course in this case the kick you have in potassium is a good indication that you are involving likely components of the crust, exotic component of the crust at depth in a magma that is mostly ultramafic and coming from the mantle, so deeper source with ultrapotassic composition. Again, the example of kimberlites, lamproites, and all other sort of ultrapotassic rocks. In this other case, you have a more complicated pattern because here there is a lot of crustal contamination that comes from the residence, time of residence of the magmas in the crust, and interaction also with a higher volume of volatiles, which of course influences and increases the complexity of this relationship between trace elements, rare earth elements, and some of the major elements. Mid-ocean ridge basalts are more reflective of the mantle signatures, so you have far less enrichment because these have the least amount of crustal assimilation, so you don't have a lot of contamination taking place in mid-ocean ridge basalts, and because of that you have that the coefficient of enrichment, which is essentially the element concentration in a rock divided by a primitive mantle composition, which is the least, it's the most primitive, so it doesn't have really influence from the crust of any kind. So you can see moderate enrichments here really, so with a maximum that is slightly over the 10, so on the order of 15 levels of enrichments for these elements. But if we look at the first two, so barium and rubidium, we have just a couple of times of enrichment, so it's roughly twice for barium and likely on the order of 2.4 for rubidium. So these are good criteria that can help us making this type of discriminations, and of course if you have a chemical analysis of a rock that is a basalt, you can distinguish the different types of tectonic settings related to that specific rock specimen. In the case of oceanic island volcanics, there are really tons of these intraplate volcanoes. One of the biggest is this Tamo volcano, and it's probably the largest volcano we have on our planet. So it's actually a submarine volcano. So it is important to be aware that all the rift systems have essentially a massive amount of volcanoes that are submerged. Usually they tend to form after a plateau has formed, and they are part of the evolution also of shield volcanoes, as we will see that they go from submarine to more submerged or subaerial conditions over time. Although this is not a permanent status, we saw that this changes over time and they will become submarine again when the activity terminates. So there are many that will be like the Hawaiian Islands, but the majority is submerged, and they form chains of volcanic seamounts which will be associated with both tectonic environments we saw, so the hot spots, but also the mid-oceanic ridges or transfer margins, depending on how you want to sort of define them. The Hawaiian chain is dominated by tholeiitic basalts with minor alkali volcanics, so that's important. So that this is a magmatic series, and it's well distinguished by the calc-alkaline series. So there are two main magmatic series, the tholeiitic and the calc-alkaline. The tholeiitic series is different from the calc-alkaline because it is essentially a series that is subalkaline, so it does have essentially a content in alkali that is lower if compared to the calc-alkaline. So for example, it does have less sodium, less potassium. One other thing that is different is also the redox state of the magma. Usually the series that is tholeiitic will be represented by a reduced magma, so low oxidation state. Instead, calc-alkaline magmas are usually more oxidized. As discussed, the chain of volcanoes that are represented by the Hawaiian Islands reflect essentially the result of hotspot activity. In this slide you see clearly a classic shield volcano, which is the Mauna Loa volcano in the Big Island, which is the southern island of Hawaii. And one thing we didn't mention in previous lecture is that there is a tendency of the shield volcanoes to keep an inclination on the order of 5 degrees in the top part of the shield, and then usually you have that these get steeper away from the summit of the volcano. It is also important to realize really the size of these massive volcanoes. This one, the Mauna Loa, extends for a diameter of roughly 140 kilometers, and it's quite tall, so it's on the order of 4,000 meters. And also, given the extensive mass of lava that is accumulated as part of the shield building process, you tend to have that there is an inflection in the crust that takes place, and so you can think of a shield volcano like essentially an iceberg. So a lot of mass is also underneath the base of the volcano, and yes, it has been estimated that the total elevation of this volcano would be double the elevation of the Everest. So effectively it's one of the tallest things that is on our planet, or the thickest things that are on our planet. So that's quite important to know because of the sort of relationship that we make between the mass and the yearly production of magma that occurs in these type of tectonic settings. So we can see here an image of some of the basaltic flows that are presently recorded on the Big Island. The Big Island, as I said, is the island that is located south of the Hawaiian chains, and it does have the most active volcanoes. We can remember, for example, very recent the 2018 eruptions that occurred in this area of the island, so the southeastern part, which is related to the Kilauea volcano. But then you have older volcanoes, so these two, the Mauna Loa and Kilauea, are the most active, so they're presently active. Mauna Loa, in reality, it didn't really erupt recently, but it still demonstrated some activity, and some of the most important eruptions date back to the 84. So in the 80s you had activity here, and now in the last few years a lot of the activity has occurred in the Kilauea. In this image here you can see how the activity takes place, because there are essentially traces in black of recent magmatic flows. So remember that these lava are basaltic, so they tend to be very fluid, and you will have little really explosive activity in this particular context. Some of the oldest volcanoes on the island are the Uala and Koala, which are on this side, so you can see the small crater here, and this other major volcano, which is characterized by cindery activity, so lots of cinder cones are found on Koala. And yeah, these are essentially volcanoes that are far less active if compared to the Mauna Loa and Kilauea. In terms of the eruption style, you can see also that the magma is escaping from rift systems. So there are rifts that essentially run through the island, which are major fractures, and these are essentially the feeders for these major magma flows. So magma flows can reach the sea, and we will see they produce a characteristic activity. You have a picture in here of some of the magma reaching the seashore and the resulting vapors and gases, which are part of some of the explosive activity that is recorded on the island. Many people tend to stand and watch this beautiful show, but yes, they have to be mindful. On the island, some accidents occurred because of the sting. So these are really hot steam, can actually cause burns to your skin, and you can even die in extreme circumstances. You can see here the rifts again with the Mauna Loa. This is a geological map. So you can see the different volcanoes. The most active part really of the island is this region, which includes also this new rift with a submarine volcano, which is called Lohihi. So Lohihi will be a future extension of the Big Island, and progressively over a million years is estimated that the activity will cease on the island, because this is part of the cycle of evolution of these shield volcanoes. They essentially are active for a restricted period of time. We can see on the order of 700,000 years to actually build a volcano of this type, and lead to essentially subaerial activities. And usually, yeah, the first part, the first 300,000 years to 400,000 years are used to actually build the shield. We will see some sort of a cartoon that shows the different processes. In this geological map, you have here a legend, you have a scale, so you get a perspective. These are, on the order of hundreds of kilometers in terms of extent of these lava flows, and yes, this is in violet are indicated the terrestrial lava flows, and then you have these blue lines that illustrate the rifts or ridges, depending how you want to call them. And yes, we have also a variety of styles of lava. Remember that when the lava reaches the seashore, quite often it becomes AA lava, so you go from Paoi into AA, depending on the slope that the lava is going through, as well as the relative interaction with seawater, which of course tends to cool down the lava. You increase the viscosity, you lower the temperature, and as a consequence of that, you change the behavior of the flow. So you have fragmental lava and submerged terrestrial lava that accumulates basically on the sides of this island. So the fragmental lava would be the more AA type. Then we have submarine lavas, which are more enriched in those characteristic pillow lavas. We will see some example of pillows again, and some of the key structures that we find in pillows. And also we have that quite often there is instability on the flanks under the coastline. On the flanks of these large shield volcanoes, you will find slumps forming, so landslides, and then you have the abyssal plains. So lots of activity also around, with a number of seamounts that include the Lohihi that has already started to produce significant amount of relatively young lavas in submarine conditions. So you have young lavas in this southern part, but also a little bit up here in the north and along the Puna Ridge, which is the one that was interested by extensive activity in 2018. Here is an example of the caldera that you find on the summit of the Mauna Loa. You can see clearly the rift zone that essentially goes across the caldera, and this is the main feeder for this lava that is relatively recent. I said eruption in the 80s are marked in black. This is a Landsat image, so you can see also different colors that represents different ages of lava flows. Of course, this is linked to the oxidation processes that take place when the lava is emitted. If you remember, I mentioned that tholeiitic magma is relatively reduced, so that's a good example of the effect of weathering. You tend to turn to red or brownish colors the lava when it's exposed to the weathering agents. Down here you can see also some cinder cones that formed along the main ridge and other lava as well. So it's important to mention the fact that usually on this type of craters you tend to, so this is a crater pit, you tend to accumulate quite a bit of lava, and in some cases like the Puo recently, we had activity that was of the type that is defined as lava lakes. So you can form lava lakes in Hawaiian volcanoes, although from 2018 there are no longer any lava lakes active lava lakes on the Hawaiian Islands. But yeah, it's important to know that you can have oscillation in the level of the magma, and so you can break these crusts that form on top of the lava lake, and usually you have very intense degassing because the magma is very fluid and it's non-viscous. It does have a low silicate amount, and as a consequence of that, it tends to liberate the majority of the gases really early. Here is an image of the Kilauea lava lake. So this lava lake is no longer there after the 2018 eruption of the Puna Ridge. It's been essentially absorbed because a lot of lava flows occurred, and so the volume of magma has decreased significantly. At present, there is actually a central lake, and that's related to the fact that the crater depressed further of roughly 70 meters, and this led essentially to an elevation that is below the water table. So, as I stated earlier, the lava lakes will be a dynamic phenomena. They can exist for a limited amount of time, but also they can disappear and then return again. And this is quite important for geologists because they need to figure out the type of interactions that are possible. So Kilauea has a recent history of relatively quiet eruptions, non-explosive eruptions, but if you have the element of water that enters into play, you can start to have situations in which you develop phreatomagmatic eruptions. So the interaction of water and steam produced through essentially the contact of water with magma can actually lead to significantly explosive activities, and in fact the Kilauea volcano is known for having had significant explosive activity in the past, in the 1700s. So there are different lithotypes that we find on a shield volcano in response to these complicated interactions that we find with seawater. So quite often at the base of the oceanic crust, we tend to develop a feeder system for the magma, and usually around the complex of so the magmatic chamber that forms, that hosts the magma, you tend to have sheeted dikes complexes that form right on top of this zone. Yes, and the zone is characterized by gabbros. So this area here is dominated by gabbros, and all these little circles are indicative of the classic shape of pillow lavas. So we have essentially on the side under the sheeted dikes, you start to have persistence of pillow lavas. This makes sense because in the beginning here you will have that you have a lot of magma that is still hot and interacts with seawater, and so in the first phases of the shield volcano you tend to develop quite a bit of pillow lavas, and then when you are in a subaerial condition, instead you have water coming from the surface and you tend to form these fissures and fracturing that is typical of lava flows at the center where you have the crater. So this would be your central rift zone, and then you have all these stratified lava flows that are at the top really of the shield volcano. On this side we mentioned hydroclastites and megaslumps. We already mentioned the fact that here the lava will interact significantly with the seawater, and so you have glassy material that develops through quenching, and this leads often to alteration that is quite common, which leads to the production of hydroclastites and these are deposits that are eroded away, altered, and will form these classic sedimentary stratifications. These often cause instabilities which are manifested with the formation of these slumps, which are essentially very shallow fault zones that are in reverse mode, so they tend to uplift the material where they form, so they are essentially at the base of hills that develop in response to the slumping of the sediments. So you are essentially removing mass on this side, stabilizing through the redeposition on dislocation and movement through flow. So these are the mega slumps. So I think we addressed the majority of the characteristics of these shield volcanoes. You have an image here that illustrate this type of structure in 3 dimension. So you have sort of your hot spot at the base that leads to magma development. So you have your gabbros that are on the side, so crystallization of the magma at depth leads to gabbroic rocks because of the ultramafic compositions of two mafic compositions of the magmas. Then you have your pillow lavas on the side, and then all the slumping materials, so fragmental lavas forming, and then you have larger blocks that result from the transport in response to major landslides, and also the subaerial basalt formation. So here it's all basaltic rocks that are more Pohoi-like. So there is a matching between the style of lava flows and the position with respect to the summit of the volcano. So closer to the summit, you will have dominantly Pohoi lavas, so smooth lavas forming, and on the sides, especially in seawater conditions, you tend to have more blocky lava forming, so you have all these blocks that results from transport and failure of the flanks. This failure is represented with sets of reverse and normal structures, which are indicated in red. So a magma system at an oceanic mantle plume, as the dust deduced from geologic, earthquake, and geochemical studies, will have a very complex structure. Some of the features, now we are going to look at some of the features. So we mentioned the pillow lavas, so you have a nice example of pillows here. So this surface is very smooth, so you tend to form crusts that are solidifying very rapidly. You can see the solidification that is also resulting in the gassing. You can see a lot of pores in this rock, which are a good indication of the interaction with water. And so rapid cooling, devolatilization will lead to these bubbly textures. Pillows usually do not really have a perfect spherical shape. They are in many cases extrusions, and so these will be elongated features, like in this example here. You can see also a lot of wrinkling related to the rapid solidification of this Pohoi relatively fluid magma. And so here you have another example of this major extrusion. So you have a number of extrusions that essentially form piles of pillows that in section we look at essentially a set of stacked channels, basically. So how does the extrusion works? You do have essentially a flow direction, so through the accumulation of lavas, quite often you tend to progressively build up what is a lava channel, and this lava channel can operate for a significant time and transport magma, and this will extend progressively until you start to reduce the amount of flow. So you have essentially a collapse of this structure. and you lose sort of intensity in terms of flow, and then you start to solidify completely the pillows and you form this highly convoluted geometry. This is not in section, these are sections through them. So in the field, at surface they will look like this, but on natural cuts of these formations you will find classical pseudospherical geometries. They are actually they need to be distinguished from other features that are also spherical. Quite often pillows will have radial fracturing. Instead, lava channels that have more intense flows will tend to have more concentric rather than radial features. An example here of a lava tube. Many times lava tube will maintain a cavity inside because of the solidification that is differential. So the crust forms externally, but you still have significant amount of flow taking place inside the tunnel. So the channel will work for relatively protracted times. Here is an example of here is an example of a lava tube, and you can see the characteristic crust, so a very thin crust forming, which is commonly related to the interaction of the magma with seawater. So you have essentially glassy material that forms on the sides of the pillow, on the margins of the pillow. And since this is glass, quite often you tend to form through weathering and alteration a lot of clays, and these are commonly called hyaloclastites. So other features that are apparent are these cavities, which are quite distinctive of pillows, and they are more related to the contraction of the magma. So you tend to have that solidification of the magma will lead to a phase of contraction, and this leads to the development of cavities that then can get filled by secondary minerals. In this example, this could be either carbonate or quartz, or even other minerals as well can be present. So a bit like the myelolithic cavities we mentioned in one of the first lectures. Here is another example of more compacted cases. So often you can recognize bubbles in the pillows, and if the pillow is subject to compaction, they tend to get also an elliptical shape. So compaction will lead to essentially asymmetric bubbles. The shape of the pillows, of course, is also a good indication of the flattening that takes place. This is related mostly to slumping, so instability, and yes, the pillows can accumulate for considerable thicknesses. In some cases, they can exceed easily the 100 meters on these volcanoes. This is an example from Canada. So the VOLCANICS with pillows that are of, I believe, Archean age, so on the order of 2.7 billion years. And yeah, the texture suggests that the water was already present at the time of formation of these pillows. So as a consequence of that, it's interesting because it gives you the feeling of the time at which water was present on our planet in a free form, and that's quite quite ancient time, so 2.7 billion years. It's quite a while ago. Are there any pillows on Mars? This is a good question. I think if we think in terms of identifying the existence of water on other planets and its obvious connection to life. So certainly from the standpoint of understanding the existence of life or water on a planet, understanding, I think, the morphology and structures of volcanic rocks can be quite useful to unravel some of these clues and questions we have. These are some other examples of hydroclastic sediment that has formed. So you see here the abundance of sediments that are interstitial to the pillows, and it's more argillaceous in composition. And here these crusts that then leads to the hyaloclastites, which is fragmented glass, and inside you can see all sort of fracturing taking place within the pillows. Some other examples of how the hyaloclastite gets layered. So often you have that these deposits tend to accumulate gradually within open space that is generated between the pillows, especially if the pillows are subject to instability, which will break the pillows and results in accumulation of clastic material. And this gets then, usually when you fragment a rock, you increase the pore space and volume of space available to sedimentation, and this, I think, is a good example of that process. So you are liberating the pillows from their original position, and then you essentially resediment material and consolidate the rock again through a variety of processes, but dominantly diagenetic processes. So essentially you generate what is called a volcanosedimentary sequence. Here is an example of a contact. So you have some significant flow that is classically sedimentary. So we will see in future lecture that address the sedimentary rocks, that sedimentary rocks can have characteristic bedding, which is a particular type of layering. So if you look at this rock here, you can recognize essentially a set of horizons and well-defined layers in the rock, but also you can see that some are discordant. If you remember, we mentioned when we were talking about pyroclastic rocks, this concept of unconformities. And so in this particular case, we have examples of another type of feature that is very similar, but usually at another scale, which is termed cross-bedding. So these are cross-bedded layers, and then you have another phase of pillows that is formed right on top of these material. So you have multiple phases. This is to say that you have a dynamic with multiple phases which might form pyroclastic material that gets mixed with other type of sedimentary sources, which are usually related to weathering of pre-existing volcanic rocks, and this material is relatively fine-grained and will get sedimented. And then you might have a second phase of magmatism that will involve new pillow lava development. Some pillows evolve progressively and tend to inflate. They can get relatively big, especially if you have relatively viscous magmas. So andesitic volcanoes in a submarine condition can form pillows that exceed the meter in diameter because of the viscosity. So magma viscosity, as well as other factors such as temperature of the magma will influence the ability to develop relatively large pillows. It's interesting to see here also the number of volatiles that concentrate on the margins of the pillow and their orientation, which is more radial. If you see, you have departing sort of sets of fractures that are radially disposed with respect to the center of this pillow. Similar thing is occurring here with a specific rim in which you develop a lot of the volatiles and you have liberation of gases. So it's quite interesting to see that, but also it's interesting to see that this pillow is losing one of its contacts and is actually connecting. So during growth you are breaking essentially the boundary existing between two pillows and you form a single pillow, preserving some of the original structure of the two separate entities. Some other examples of broken pillows: sometimes the crust can break as stated, so you have examples here of all the fragmentation with isolated clasts that have developed and fragments that will then be altered likely and results in the production of either of hyaloclastites or hydroclastic sediment. Often you get these cases in which the breccia is more evident. So if you are away on a submarine environment and you have slumps taking place away from the center of the volcano, well, you can form these brecciated pillows which are essentially fragmented by the effect of the landslide. So they can be part of this landslide and therefore accumulate in non-autochthonous locations, so away from where they were originally formed. Sometimes the activity leads to relatively smooth surfaces, so Pauhoi lavas will form, and also this is found in the Archean camp volcanics, similarly to what happens today in the Hawaiian Islands. So in this area of Yellowknife, you will recognize these lava top flows, which are also characteristically cracked by a variety of fractures, which are usually extensional joints. These are some examples of the lavas that we find in recent eruptions of the Kilauea volcano, and so you can see how this Pauhoi lava is really fluid and form these lava channels in which the lava can travel for really relatively high speeds, so on the order of 60 km per hour quite easily. And often you form levees on the side of the lava channels that will have these Pauhoi solidified lavas forming ropey textures. You can see some of the ropey textures here on the top of this channel because there is a crust that is forming on the top part, and then suddenly the change in velocity that takes place and this low in temperature in terms of sort of source and vicinity to the feeder leads to cooling down, and the cooling down leads to the formation of clinkers, so blocky lava, AA type lava develops, and some example of that are present in this part of this figure. So of course the interaction is very destructive, so destruction of vegetation takes place as well as any other human built construction, and this is why these are relatively dangerous situations that needs to be constantly monitored, and risk has to be evaluated, and then precautions should be taken to prevent any loss of life as well as loss of infrastructure. Some other examples here of, I think a car has been sort of destroyed by activity in a AA lava flow. So remember that AA is much more difficult to block, and it's often leading to this type of destruction. Here is the contrast in which you have sort of Poi lava that is extremely ropey, so you can see the surface looks like a drape of tissue, and that's all the falls that develop in relationship to the differential velocity that exists in the lava flow. These lava flows are quite laminar and thin, so the lava can form these large levees and expand significantly because it's very fluid. Some other example of these Hawaiian style eruptions with lobated lavas, and you can see here that the wrinkles are curved as an indication of the differential velocity in this tongu of lava, in which we have sort of slower velocities on the side and then a more higher central velocity, which imposes this curvature because this lava is moving slower and slower while it's solidifying. At the back, a lava fountain, another indication of close proximity to the main crater, which is usually, as I stated, represented by activity that can be explosive and usually involves a lava lake. But it could be also that this lava is very close to the sea, and so in some other instances also we have fountains of lava forming, which is when the lava reaches seawater. This is an example of an AA type lava, so you can see it's mostly clinkering, represented by blocks of different size, which is essentially the crust breaking down because of the mass of lava that is pushing, and we have this clinkery appearance that is characteristic of these AA lava flows. Another example of the activity I was mentioning, so steam gas eruption, can result from lava that is flowing directly into seawater. And you can see here different streams of lava that is straight into seawater with a significant production of steam, really hot steam, which can cause significant damage to people, mostly that are trying to sort of see this phenomena. So you have to be very careful. Lava fountain at night. These lava fountains are really representative of the explosive phase of these activity. We have to say that this activity is a minor component of present-day eruptions in the Hawaiian Islands. However, when the submarine volcano is developing into a mature shield volcano, this type of lava fountains will be much more pronounced in terms of volume, just because of the extensive interaction with seawater. The close interaction occurs because there is a stage in the development of the shield volcano in which the eruptions are occurring at sea level. So a lot of water is interacting with the magmas, and you have also a lot of caldera activity that develops in a continuous fashion. This phase will end when the elevation of the volcano will exceed usually 4,000 feet, and this essentially will avoid this constant interaction between the sea and the venting locations of the volcano. Okay, We can review some of the stages here. So the evolution of hypothetical submarine volcanoes is represented here with a number of features with a different degree of maturity. We start at the top here with the development of pillow basalts, which are fed by a magma chamber, and you have a number of dikes at the bottom. After approximately 400,000 years, you are still developing significantly the shield, and you start to have this development of more extensive city dike systems on top, as well as sets of normal structures that are sort of stabilizing the flanks of the volcano. Again, after a million years roughly, we touch sea surface, so we reach a stage in which we have that the water is no longer present on the central part of the volcano, and you start to develop all these other products on top. So the famous Pahoehoe lava and AA lava, and then you have flank cratering, cinder cones, and other forms that are illustrated here, including slump blocking and also slump structures and folds as well. Once you have exhausted the source of energy, the last phase is actually a reversal in which the water claims back the central part of the volcano, and we start to develop usually a rift system, and you form an atoll, which is quite commonly present because of the elevation and the fact that corals tend to grow in the photic zone. So they will form a ring, usually of corals, that surrounds the summit of the marine volcano. And this is linked to this process of drifting. So progressively the volcano will drift away from the source plume, and this is why you're losing through erosion and weathering the top part of the volcano, and it gets submerged again. So we were mentioning that there is a shift or a drift of the crust that leads to a movement relative to the central hotspot. You have a cross section here that examines the style of magmatism, and it's changing in response to this drift. We have here an example for the Hawaiian Islands that shows a drift of roughly 10 centimeters per year, and we have here listed the top of the mountains or volcanoes. So we have the Lohihi here, the Kilauea, Mauna Loa, Mauna Kea, and also one of the eastern Maui volcanoes, so the main volcano that is on a very proximal island that is right north of the big island, which is Maui. So you can see here the moho, so the oceanic crust is relatively thin, on the order of roughly 10 kilometers, and down here we have a series of isotherms that shows you the temperature of the mantle, and the hot plume is clearly causing an anomaly because you have essentially an extended high temperature domain that is forming, which justify the areas and volumes of magmatism that are identified by these circles. So we have essentially different stages in which we will produce different rock types or melts with variable composition. The key aspect is that here you tend to have low volume of melting. So in the pre-shield stage, which is this one we are sort of illustrating with this slide, so down here in this other diagram that shows time versus volcanic growth rate. So we have that we emit small volumes of products, and this small volume affects also the composition of the magmas, which are quite commonly alkaline basalts. So they contain, potassium and other alkalis, and that's commonly because there is not enough really magma to have this classic tholeiic signature. So if we change slide, in this other example, instead, we have the Kilauea and Mauna Loa that are really part of this key stage in which you have development of more than 32,000 cubic kilometers of tholeiic basalt. So that's the key building stage for the volcano, and so you have massive amount of lava that are emitted by the Kilauea and Mauna Loa because they are right on the hot spot. Okay, so this is of course translated in products such as eruption of pillow lavas, and quite often you have a condition in which these magmas are more fluid if compared to the alkaline basalts that are emitted in the pre-shield stage. After this phase, you see here that the plume is stretching in this direction with the isotherms stretching, and so you still have magmatism in the earlier volcanoes like in the Eastern Maui, and this volcano is far less active, so you can see even a smaller volume, but pretty much we have a similar type of magmatism which is comparable to the pre-shield stage. So it will be an alkaline tholeiic basalt, so usually quite potassic magmatism. So the post-shield is an alkalic stage, and the amount and degree of partial melting becomes relatively low. So you have a return to an alkalic lava production, and so you end up having sort of minor explosive volcanism as a consequence of this process, and of course a reduction in the eruption rates. So commonly in terms of time, you can think of this post-shield stage as occurring roughly 300,000 years after the main tholeite stage, but up to 2 million years later. Quite often, once the islands cease completely the volcanic activity, they are strongly affected by erosion. So after 4 million years, you have this example from Kauai that is deeply dissected by stream erosion. So all the river systems that develop on the shield volcano during any rainfall or during the rainfall seasons will affect and dissect quite easily, and you can see this reddish color, which is an indication of the level of weathering with a lot of oxidation of iron taking place. Remember that the basalts are ferromagnesium rich, so you will tend to oxidize the iron, which is an immobile element, and it will sort of stay and show up as this classical rusty staining on the rocks. Further down the track, the island will be completely eroded, so you will be left with relatively small islands with no activity, and gradually the shield volcano becomes a submarine seamount, basically. But the process will take, several million years. Okay, we have reviewed some of the details of the Hawaiian volcanoes, and so that this is like a cyclic process. We're going to compare it now against mid-ocean basalts, so the one that forms on the Atlantic and Pacific rift systems, or at the boundary between the Australian plates and the Antarctica. So there is also an Atlantic rift system that runs down there and then up into the Indian Ocean. So here you have an image of Iceland, dominantly covered by extensive glaciers. This is because of the high latitude of this terrain that is thought to have been forming in response to the Iceland hotspot. So it's a complex terrain. We saw that already there is an intersection between a plume and basically an oceanic rift. So you can see here the traces of the geology and the alignment on some of the geomorphological forms highlights actually a trend that is a trend of normal structures or normal faults that form a central graben or a series of grabens that do reflect the location of the rift system, which essentially runs through the island and then curves to a more northerly direction in this domain. So here is also famous for volcanoes that were active in the 1700, like the Lucky Field. So there is clear evidence, as illustrated in earlier lectures, of the volcanic activity associated with this rifting. But yeah, the history of Iceland is an history that starts roughly 60 million years ago. So it stretches back to this time and involves the mantle plume and its interaction with this mid-ocean ridge. Roughly at 60 million years, we have sort of a new mantle plume that rises and creates a sort of a large province, which is a flowed basalt province similar to the Columbia River province that we saw earlier, where we find the Yellowstone. And this is this one here indicated in purple. So we have extensive basaltic flows, and what they think is that progressively over time, during the expansion that occurred along the rift, we had essentially a stage in which there is a transition or a switch in the rift system, and it goes from being originally between North America and Greenland in actually transecting through Europe and Greenland. And you can see in this second image at 30 million years that the switch has occurred, and we have this sort of bridge that connects these two basalt provinces, which are very similar. So we find the same basalts in Greenland and also in Europe, on the northern part of England, for example, and partly in Norway. And yeah, this is a good indication that this was a major spreading center. And after this, the supply of magmas has continued and led to the piling up of several layers of pillow lavas and plateaus that led to the formation of Iceland. So you have here a proto-Iceland, so initial stage of formation, and at present date we have a much more developed scenario in which Iceland is essentially growing with the rift because of the intensive activity of the plume. So essentially Iceland sits sits astride the mid-Atlantic ridge and it's continuously rifted apart. Of course, this is particularly interesting to geologists because you can essentially study an exposed rift system in a subaerial condition, which is a rare occurrence because the majority of the rift systems are located under the ocean. Okay, so there is still volcanic activity that takes place in this region, and here we have sort of another more detailed elevation map of the bathymetry, which illustrates the distribution of transform faults and essentially the different components. So the oldest crust in Iceland is 20 million years old, which is of course an indication of the extent of subaerial, likely subaerial materials that represent a relatively recent phase of this plateau development. So you can see here, looking at the bathymetry, that this coastline in reality extends for a significant distance away from the main island and forms a platform that is likely of similar ages. Here we look at the geology of Iceland. We were seeing already those linears in the geomorphology extracted from Landsat data, and here is just a more detailed representation of the geology showing the area that is dominated by the rift system. So we have two separate systems in the southern part. One is close to Reykjavik and the other forms the Lucky Field, and then you have essentially the deviation of this field to a northerly direction in the Krafla area. So this is quite exciting terrain and beautiful, and Iceland sort of straddles the mid-Atlantic ridge. It consists of 2 to 35 kilometers of older olivine-tholeiitic basalts flanking a central rift zone. So everything is really basaltic in composition in this domain, and we have that progressively we find older basalts at the edge of the rift system. As the linears suggest, the central zone has numerous northeast trending extensional fissures, which are similar to the Hawaiian volcanoes, part of the rift systems that feed lavas to the island, and so form lava flows and extensive plateaus in response to these feeder systems. So picrites are erupted, which is a good indication that the magma comes from deep, since these are very close to mantle composition. So they have elevated magnesium, for example. And also you have alkali basalts that quite commonly are formed away from the main rift zone. So there is an analogy with the Hawaiian Islands, in the sense that the amount of partial melting and the mantle supply of heat and magma will be the dominant control on the type of fractionation that takes place. We have again tholeiitic basaltic magmas, which are however generated at relatively low pressure, so less than 30 kilometers, which leads to increased sort of iron contents, and yes, they erupt from the central volcanoes, one of the key volcanoes that has a long history of eruption is the Torfjokul, and also I think these other, the age of GEOL. So we will look also at age of GEOL and discuss the type of activity. So in this case we have the first phase of this eruption, and we see a lot of steam gases liberating, and this is essentially an activity that occurred in 2010, and it's related to a fissure that roughly opened 450 meters in length, and it was running northeast to southwest, so similar to the Lucky field. In fact, it's south of this area, so immediately south of the Lucky, and we have essentially 10 to 12 erupting lava craters that were active at the time, with relatively alkalic and olivinic basalts. Temperature on the order of 1000 degrees, and these were forming steamy eruptions with lava fountain activity. You can see here the formation of lava cinders and splatters that will be forming mostly cinerites and lapilli. The phase 2 of this volcano occurred in April 14, and you can see that because a lot of water was involved through the melting of a glacier that characterizes many of the Iceland eruptions, you tend to have these phases of explosive activity in the beginning, and you are essentially adding water progressively to the magma, and this increase the amount of steam and triggers potentially explosive eruptions. So similar a bit like to the activity that we saw for lava lakes. Whenever you have enough water or snow or ice, you can actually increase the amount of volatiles in the magma and cause a significant explosive activity. On the 17th of April, we have that the explosive phase of the summit eruption increase its power and start to develop a very tall column of tephra, which is again very close to an eruption that I would compare to a Vulcanian activity, because you have several kilometers of tephra ejected in terms of elevation of the column of tephra, and so this is definitely a relatively explosive activity which could correspond to a wave between 3 and 5. It was driven by the expansion of magmatic gases and by steam explosion in the crater of the volcano, which is expected. And there were recorded lightings, which are often the result of the buildup of static electricity because of the attrition that exists between the different particles that are comprising the tephra. The second eruption phase for the Eyjafjallajökull occurred also on April 20, The lava flow determined to have commenced on the 21st of April 2010 melted a significant amount of ice north of the main crater and generated a significant amount of steam. But yeah, mostly we have an activity that is a lava fountain, so similar to a strombolian activity, and so you are having more quiet eruptions, which is expected because quite often the column of magma in a volcano on its top part is particularly rich in volatiles, and then at the bottom you have less volatiles, and this is obvious. It's a function, you know, of the difference in density. So we saw the process of fractionation and convection that takes place, and so the gas is usually concentrated at the top of the magmatic chamber. What does that mean? It means that the earliest phases of eruption usually release the majority of the volatiles. Subsequently, the volcano will be much more relaxed, and therefore the style of eruption will mutate in response to the lack of volatiles. Another large chimney on May 5th and 6th as part of the second phase of eruption, and so we have a shift back to ash production. Of course, these type of eruptions are relatively cyclic, and so we have different phases that takes place and they alternate. And the ash cloud rose to between 5 and 6 Ks, and on May 17th it continued southeasterly, heading off to Europe basically. So often you get issues with this volcanism in Europe, and you need to suspend flights because the volcanic ash is terrible. If it gets into the engine of an aircraft, it will completely destroy and melt with actually the blades that are within the engine, and so it's very dangerous. And then we have a return to quiescence. 70 to 80 million of cubic meters of magma were erupted. Ash was also ejected on May 24 and 25th, but after that phase we have essentially that the volcano is just emitting small amounts of steam. And this concludes our lecture for today about the different types of volcanism that occurs in the Hawaiian Islands and also on Iceland. So we have seen a lot of close correlations in the style of magmatism. I would say that the main difference here is that the mid-oceanic ridge have a much more protracted activity, and it's much more cyclic. So it is essentially the seasonality and the interaction between ice and magma that will condition the style of volcanism in Iceland. Instead, in the Hawaiian Islands, the process is more like a single cycle in which we start building up the volcanic shield, we get into a subaerial condition, and we have mostly basaltic magma production that is mostly, fluid and really doesn't involve a lot of explosivity unless we are very close to the coastline, so we have interaction with seawater, or we have phreatomagmatic eruptions in exceptional cases on lava lakes. But most importantly, this volcanism will find an end within the million years scale, and will terminate, and simply the hotspots will move away, or vice versa. The islands will move away from the center of energy, and in response to that, these systems evolve quite rapidly in geological sense. And so you don't have extremely continuous magmatism that exceeds the 100 million years or more. So oceanic rift systems are also more protracted over time, and they represent a major area for the production and dissipation of energy on our planet. So I hope you have captured sort of these two distinctions, and you sort of now understand the different tectonic environments where extension brings up to the formation of magmas and igneous rocks of variable composition. In conclusion, I would say that the two environments are also distinct based on the different types of rocks that tend to form in this context. And I would say that the Iceland case is more explosive in a way, because you have those steam-rich eruptions that involve quite a bit of explosivity. And so we will have pyroclastic rocks and lahars that form on the Iceland volcanoes, which are rather unlikely to form in the context of the Hawaiian volcanoes like the Big Island, where we have those Pahoe lavas that essentially dominate. So there is more alkalinity, more siliceous magmatism, and in response to that we get tufaceous material accumulating in the Iceland case.